Welcome to the next session of our discussion on greedy algorithms. Last time we talked of basic properties you need to look into before designing a greedy algorithm. If you recall, there were two important properties. One was greedy choice property, and the second one was optimal substructure property. You need to look into these two properties in order to design a greedy algorithm. So today we will look into another algorithm which is called Huffman coding, and we will see that how Huffman codes uses a greedy approach to solve the problem. So let's say you have a file with the following content. So you have a text file with the following content where it is written, there was a brown crow, he was very intelligent. So I'm just writing some words, maybe some sentences, okay? And what I see that how many times a particular character appears in this entire text. So in this text we have character A appearing 3 times. So if we look into, we see that okay, character A is going to come 3 times, okay? So 1, 2 and 3, okay? Character B is coming only once, character C is only once, character E is 6 times, okay? So 1, 2, 3, 4, 5, 6, okay? And so on. So you essentially look into how many times a particular character appears, okay? So yes, the problem is you want to encode this file such that each character is represented by a unique binary string which we will call as code words. So for every character you want to essentially give a unique binary string which is called code word, and you want to encode this whole file. Of course, your objective is to encode it such that the size of your encoding is minimum, okay? So that's what we want to optimize here. Recall, when do we apply greedy algorithm? Whenever we have to solve a optimization problem. So here the optimization problem is we want an optimal encoding such that each character is represented by a unique binary string called code words, okay? So let's say if we use fixed length code. So since we have 16 characters in our example, previous example we had 16 characters, and you want to encode it, and let's say that you go by the most simplest thought process, thinking that okay, there are 16 characters, that means I can represent 16 things using 4 bits. 2 to the power 4 is 16, okay? So I will say that okay, I will fix a code, a 4-bit code for each character, okay? Now in the entire file total there are 38 characters, right? If you add up all these frequencies, you will see that this adds up to 38. So all these 38 characters, and each character is having 4-bit representation in this fixed length encoding, then how many bits you will require to encode the whole file? 38 characters are there, right? Total 38 characters are there. Each character is taking 4 bits, so total 152 bits, right? So your file size becomes 152 bits, okay? Your encoding. Question is, can we do better? This is the simplest encoding technique, and we get 152 bits for this particular file. Question is, can we do better? Okay, and apparently the answer lies that there is, if you do a variable length code, you can do considerably better than a fixed length code. Okay, now what is a variable length code? Essentially you look into the pattern, you see that a particular character which appears frequently, very frequently, that means the frequency is very high, we should use perhaps a shorter code word for it. Whereas a character which appears many times, not that many times, it's infrequent, okay, we will use a long code word. So give a frequent character short code words and infrequent character long code words. Okay. So for example, let's take an example. I don't want to take again this 16 characters, just makes it too large. Let's say in a file we have only 6 characters, A, B, C, D, E, F, let's say. Okay. And frequency of A is 45,000, frequency of B is 13,000, frequency of C is 12,000, D is 16,000, E is 9,000 and F is 5,000. Okay, so you can see that the most frequent character is A and the least frequent character is F. Okay, so this is the least frequent character and this is the most frequent character. If I use a fixed length code, now notice there are 6 characters you need to represent, A, B, C, D, E, F. If I use fixed length code, how many bits I will require? In order to represent 6 different patterns, you will require 2 to the power 3, that is 3 bits, right? So, because 2 to the power 3 is 8, more than 6, and if you take 2 bits, that is 2 to the power 2, which is 4, which is less than 6, so you cannot use 2 bits, you have to use 3 bits. Okay, so let's say you give A the code 000, B as 001 and so on. So every character gets 3 bits. Total how many A's are there? 45,000 A's are there. So if we count how many bits will be required to encode this entire file using fixed length encoding, 3 times 45,000 plus 3 times 13,000 and so on. This entire total file is having 100,000 characters. Okay, so it has 100,000 characters. Each character takes 3 bits, so total 300,000 characters it will take. Okay, or sorry, bits it will take, not characters. 100,000 characters are there. This is the number of characters. Okay, but this is the total number of bits. Okay, because each character is taking 3 bits. If I use fixed length, let's see what happens when we use variable length. Let's say A is the most frequent one, right? We can see A is the most frequent one. So we'll say that we will use a very short code for A. So we use 0 for A. Okay, for B we use 101, a 3-bit code, C 3-bit code, D 3-bit code, and let's say the least frequent character is 5,000. We use a more number of bits there, so we use 4 bits, 1100. Okay, so if I do that, now if you notice that how many total characters I will require, or how many total number of bits I will require, 45,000 times 1 plus 13,000 times 3 plus 12,000 times 3, right, and 16,000 times 3 plus 9,000 times 4 plus 5,000 times 4, that many bits, which turns out to be 2,24,000. Okay, that many bits. So you see, previously using fixed length encoding, you were spending 300,000 bits, whereas using variable length encoding, you ended up with 2,24,000 bits. Okay, so there is a significant improvement there, nearly 20% improvement is there. Okay, so it can be proven that variable length encoding can do better than fixed length coding. Now we will assume here that we will be only looking for something called prefix codes. So what is a prefix code? We consider here only codes in which no code word is also a prefix of some other code word. So it cannot happen. What it is saying is I cannot have A as 0101 and B as 10101, right? Because that's the prefix. Sorry, in this case, it has to be prefix. So, this one should be here. Okay. So that is not allowed. So we consider here only codes in which no code word is also a prefix of some other code word. That is not allowed. Okay. So such code words are called prefix codes. Even though, we are saying the word prefix codes, but it means that no code word is also a prefix of some other code word. Okay, fine. So these are called prefix codes. So if you have a prefix code, if you encode your file using prefix codes, it's simple to decode. For example, if you give this example 001011101, that's the bit string, that's the encoding. Now I want to decode it. Now I can, if I look into the variable length encoding, I see that, okay, it starts with 00. So first 0 corresponds to A. Then I have 010, okay, 11101. Now notice that there is no other code word which is starting with 0. So immediately you know that, okay, next one is 0. Then you see that, okay, what is left? 1011101, right? This much is left. Now if you look into, you immediately see that, okay, 101. So you put 101 there. Then what is left is this portion. 1101, and you see that, okay, 1101 is nothing but E. So that's the remaining code. So this turns out to be AABE, right? Okay, so you can decode the file very easily if you use prefix codes. Okay, so decoding needs a convenient representation for the prefix code so that we can easily pick up the initial keyword. So the idea is, given any encoding of a file using this variable length code, I should be able to decode it easily. How do I decode? I should be able to decode the first portion easily, okay? Then remaining I work on recursively, okay? So the way to do this is, of course, in order to do that, I require a convenient representation of my prefix code. So what we will use is a binary tree for this prefix code whose leaves are the given characters, which provides such a representation. So if you decode using this binary tree such that their leaves, the leaves of the binary tree are the given characters, then you will see that it's easy to decode. So just look at an example, the same example which we are doing, A. So here, first of all, we have a binary tree. Every node is having 2 children. Okay, if you see, in fact, every node is having exactly 2 children. Okay, either 0 or 2. So this node is having 2 children. This node is having 2 children. This one is having none. Okay, these ones are none. So all of these leaf nodes correspond to some character. What is a character here? Character corresponding to this leaf node is A, whose frequency is 45,000. I've just ignored the 1000. Okay. Then if I look into this one, okay, this is essentially corresponding to the character C, whose frequency is 12,000. This one is the next leaf node, which corresponds to the character B with frequency 13,000. So you notice that every leaf node is corresponding to a character with their given frequencies. Okay. Also note that, this is the representation of the variable length encoding we just showed here. Right? Here A, B, C, D, E, F, we showed a certain encoding there in this bottom row. That's the variable length encoding. And this binary tree is capturing that encoding. So how? If you notice, corresponding to each of the internal nodes, you have a left child and a right child. You assign corresponding to the left edge bit 0, corresponding to the right edge bit 1. So now notice what is, so you can get the code for A by traversing from the root to that node. So and the corresponding code word is nothing but the code words of the edges, right? So let's say A. What is the code word of A? From root, if you have to come to A, it is 0. So for A, it is 0. For B, if I have to come to B, I will come like this, right? So this is 1, 0, 1. So code word for B is 1, 0, 1. Code word of C is 1, 0, 0. So code word of C 1, 0, 0. Okay, so 1, 0, 0. Fine. Okay, so you traverse from the root to corresponding leaf. In between whatever are the edges, you pick up those codes that will give you the code word for the character. Okay, that's the binary tree representation of your prefix codes. Okay, also notice that corresponding to each of these internal nodes, there is an assigned number there. So for the root, it is 100. What is it? It's nothing but sum of the frequencies at the bottom level. Okay, so if I look at this internal node, its assigned number is 14, which is nothing but 5 plus 9. Total frequency is 5 plus 9. So 5000 plus 9000, 14,000. So this is representing 14,000. This one is 16,000. This is 14,000. So this one is the internal node which is having frequency 30,000. Okay. Similarly here, this is 12,000. This is 13,000. So this is the parent node of these two children. So this is 25,000. 25,000 and 30,000 together makes 55,000. 55,000 and 45,000 makes it 100,000. Okay, so that 100,000 is our total number of characters. So these are nothing but the frequencies, and you have nicely represented your prefix code using this binary tree. So essentially, the question is to find an optimal code, and an optimal code for a file is always represented by a full binary tree. So you can prove that an optimal code for a file is always represented by a full binary tree in which every non-leaf node has two children. Okay, so we will not go into that proof, but we will take it granted that that's true. Okay, so let's say you are given C alphabet. So C is the alphabet from which the characters are drawn and all character frequencies are positive. That's your assumption. Okay, then the tree for an optimal prefix code has exactly C leaves and C minus 1 internal nodes. So if you notice that in this previous case, all the leaves were corresponding to some character. So we had 6 characters total. So C was nothing but, this character alphabet is A, B, C, D, E. So there were D, E, F. Okay, fine. So there were 6 characters total. Each one of them corresponds to some leaf. How many internal nodes are there? You can see 1, 2, 3, 4, 5. So exactly, C minus 1 internal nodes are there. Okay, so that's what it is saying, that you will have C minus 1 internal nodes. Okay, I think this should be here. Okay, and C leaves. So given such a tree which is representing your optimal prefix code, you can compute what is the cost of the tree. Okay, how do you compute that? Corresponding to each character, you need to know that what cost of the tree is nothing but how many bits will be required to encode the entire file. That's the cost. You have essentially represented it as a tree. Okay, your entire encoding you have represented as a tree. Now the question you are asking is, what is the total number of bits required to encode the file? Okay, which is nothing but what is the frequency of each character and what is the depth of that character C in the tree. So if you look into your previous example, The code word for C is 101, which is nothing but the depth of it, right? From the root, how many edges you have to traverse? 1, 2, 3. Okay, so you have to traverse this edge, and this edge, right? Okay, so 3 edges you have to traverse. So depth of the tree is 3, right? So how many bits I will require? Total number of bits. You take the frequency of characters, you look into every character, look at its frequency, and then you say that, okay, how many bits will be required to encode that character? The encoding is nothing but the number of bits required to encode that character is nothing but starting from the root, how many edges you traverse, which is nothing but the depth of the character in the tree. Okay, so C times frequency times DTC, and you sum it over all the characters, you get the cost of the tree, or essentially the total number of bits required to encode the file. Okay, so now that's been given, so you have to find an optimal code. Okay, so an optimal prefix code. You have to find an optimal prefix code, and we will do so using something called Huffman coding. Okay, so first thing you notice that, let's understand that how this Huffman coding algorithm works. So C is your alphabet, N is equal to the size of C, that means how many characters are there in your alphabet, and then what you do is you form a priority queue, where the priority is based on the frequency of the characters in C. Okay, so Q is equal to C, we have said, okay, which is nothing but, so Q is the priority queue. It's a priority queue. Fine, okay. Priority queue, and the key is essentially the frequency. Then what you do for I is equal to 1 to n, you iterate for only n times. What you do? You allocate a new node Z. You create a new node Z, and then what you say that, okay, extract minimum Q, that means extract the character with the minimum frequency, and let's call that as X, and let's assign it to left of Z. Okay. So the minimum, so I am creating a node Z, then in my queue, which is having all the characters and their frequencies, you pick up the one with the minimum frequency and say that, okay, let's say that's X, and it's going to be the left child. The right child will be the second frequent one or second infrequent one. Okay, so you extract minimum of the queue again, so extract minimum will now give you the second minimum, so you call that as Y, and that becomes the right child of Z. And then you set the frequency of Z as frequency of X plus frequency of Y. And then what you do? So you just formed a part of the tree, okay? And what you do? You insert within Q this node Z, wherever. So you got a number now here, which is the frequency of Z, which is nothing but sum of the frequencies of X and Y. And you essentially put it in your priority queue, which is basically sorted by the frequencies. So you will put it in your priority queue, you will insert, and it will take its position. Fine, okay. So now what you do is, and you do it for n times, you keep on doing, at the end you say, okay, return the extract minimum queue. That means you will extract at the end the minimum of your queue, whatever is left in the queue, okay, which is nothing but root of your tree. Let's see how this becomes the root of the tree. So let's take an example. So F, here we are taking the same example, which is the least frequent character F. Recall, it has 5000 frequency. The next least frequent character is E, which is 9000 frequency. So this is sorted in increasing order, in terms of frequency. So that's your priority queue. Okay. Then what you do? You pick up the, you first frame a node Z, and you say that, okay, out of this queue, so this is my current queue, extract the minimum. So a minimum is F, make it left child. Then what do? You again extract minimum out of this queue, and then you make that one as your right child. Okay. What is the frequency here? That frequency is nothing but sum of frequencies of these two. So this is 14. And then what you do? You put this guy in the priority queue at the right place. Okay. Remember, whenever you are doing extract min, this 5 will be taken out. Okay. This F will be taken out. This E will be taken out as soon as you call the extract min. Okay. So they will not be there. And then you create this new node Z and you push it inside this priority queue at the right place. So now, what is the minimum frequent one? 12. Next one, 13. Next one is 14. So this is the node Z, which is having two children, F and E. Okay. Now let's do the exercise again. So this is the first iteration. Then you will go back. Okay. Again, pick up the least frequent from the queue and the second least frequent. So least frequent is C, second least frequent is B. So 12 and 13. So least frequency becomes left child, second least frequency becomes right child. You create a new node with the frequency which is sum of these two frequencies, 12 and 13. So you got 25, and you then push it in the priority queue at the right place. So 25 comes in there. Notice that 14 is now at the head of the queue. Okay, because 14 is the least frequent one. That's the least frequency. Then again, what is the next? So we have reached to this position. What is the next two least frequent ones? This 14 and D. So I will create a new node, Z, whose left child is the least frequent character or node, so which is 14. The second least frequent is D, which is 16. So that becomes the right child, and I create a new node Z with the frequency 30. And then I push 30 at the right place in my priority queue. So now the priority queue is having 25, 30 and 45. Okay. So after that, the next step is again to extract the minimum frequent one and the second minimum frequent one. So minimum frequent one is 25, second minimum frequent is 30. You will create a new node which is Z, whose left child is 25, right child is 30, and essentially then you push it into your priority queue at the right place. So it comes after A, 45. So the A is having frequency 45, which is less than 55, the frequency 55. Then one more step, you say that, okay, now again I have to extract the minimum one and the second minimum one, which is 55, and then you create a new node which is Z, which is having the sum of the frequencies of the left child and right child, which is 100. Left child is the least frequent one, a 45, and second least frequent one is 55. Okay, so I got my tree, and notice that this is the same tree which we have shown you. The variable length encoding of each character you can now easily get. So what is it for A? A is 0. For B, it is how much? 1, 0, 1. For C, it is 1, 0, 0. For D, it is 1, 1, 1. So 1, 1, 1. For E, it is 1. You always start from the root. 1, 0, 1. So 1, 1, 0, 1. How about F? F is 1, 1, 0 0. So 1 1 0 0, that's F. Okay, fine. So that's the prefix code we used, and that's the binary representation which we get from the Huffman codes. So if we use heap data structure to represent or implement this minimum priority queue, then you're constructing the queue will take order of n time, and your other operations, other queue operations, priority queue operations which are there in this for loop, they will take order of log n time. And since your for loop is running from 1 to n, that means it is running n minus 1 times. So total time taken is order of n log n. Okay. So the complexity is nothing but n log n. Okay. So I hope it is clear that how we are creating this Huffman codes. So Huffman code is this algorithm. Given an alphabet set along with this frequency, what it produces is an optimal prefix code using greedy choice. Okay, what is the greedy choice? It says that, okay, pick up the one with the least frequency, make that one as the left child, pick up the one with the next least frequency, make it right child, and create a new node with the frequency of sum of these two frequencies. So that's the greedy choice. Okay, so what we need to prove is that indeed this Huffman code gives the optimal prefix code. Okay, so we will prove it using both the greedy property and the optimal substructure property in the next session. Thank you.